All right, so on to 4.4 about de Moivre's theorem. So this is a really cool theorem. This is one of my favorites. And one of the reasons that I like it so much is that it ties together algebra and trig. So let's get into it. I just think it's a really cool theorem. And it's sort of the last tool that we're going to add to our toolkit in this class for finding zeros of polynomials. Okay. So first of all, recall that a complex number has the form a plus bi, where a and b are real numbers. By the fundamental theorem of algebra, we know that p of x equals x to the fourth plus 1 has 4 complex zeros. So let's try to find them, right? Now, as we discussed in the previous section, fourth root of -1 must be a 0, but it's not written in the orthodox, a plus bi format. Now, we could play around a little bit. We could say fourth root of -1 is the same as -1 to the 1/4 power, and then we can notice that we can rewrite that as -1 to the 1/2 to the 1/2, or in other words, is the square root of -1. Square root of -1 is just I. So fourth root of -1 is really just the same thing as the square root of I. But the square root of I is still not written in the form a plus bi. Okay, you're not allowed to have a square root around the I. So in other words, we still haven't even shown that this is a complex number. And the other problem is that this would only be one solution. What about the other 3? Right? There should be 4 of them, right? There should be 4 solutions. So to answer these questions, we appeal to a result called de Moivre's theorem. And to understand de Moivre's theorem, we first need to review how to write complex numbers in polar form. I say review. If you've never seen this before, then this is brand new information to you. But I know that you go over this in trig. So if you have like a formal trig class, then you've seen this before. If you didn't, then this might be new information. But here's how we rewrite complex numbers in polar form. So first of all, we can graph complex numbers in the rectangular plane by treating a plus bi as an ordered pair, ab. In this case, we call the x-axis the real axis, and we call the y-axis the imaginary axis. And the Cartesian plane, we call it the complex plane. But really, it's just a matter of graphing ordered pairs. So for example, 2 plus 3i. Right? 2 plus 3i would be the point 2, 3. It would correspond to the point 2, 3. So all of the real numbers fall on this number line here, right? The x-axis is like the real number line. It's the real axis. But complex numbers are not on the real number line because they're not real, right? But they do have real parts, right? So they have so 2 plus 3i corresponds to the point 2, 3. This is the imaginary axis, right? -3 plus 2i would look like that. 4 would look like that. -I would look like that. Okay? And -2 minus 3i. -2 minus 3i would look like that. Okay? So this is how we graph complex numbers in the polar, or in the complex plane. Now, once the complex number has been plotted in the complex plane, we can describe its position in a different way. So rather than describe it in terms of how many vertical and horizontal units it is from the origin, we can describe it in terms of its distance from the origin, right? So not like its vertical or its horizontal and vertical distance, but just its direct distance, right? The direct line from here to here. We can describe it in terms of that distance and the angle that its ray makes with the positive x-axis. So this angle right here. Okay. So we can describe this point in terms of this distance and this angle instead of this distance and this distance, right? So I gave us a space to draw a picture. I suppose I should do that. So we can describe that point by looking at this distance, which I'm going to call r, and then looking at this angle, which I'm going to call theta, and this is the point AB, right? So a couple things to note. First of all, theta satisfies the equation tangent theta equals b over a. right? Because if you make a little right triangle out of this, we know that this is b units and this is a units. Tangent theta is b over a. Now that's not the same thing as saying that theta is tangent inverse of b over a. That's true if you're in quadrant 1, but if you're in quadrant 4, theta is not tangent inverse of b over a, because tangent inverse of b over a is going to give you a negative angle, and we want theta to be the positive angle, so we want it to be the other one. So theta will have the same reference angle as tangent inverse of b over a, but it's not necessarily tangent inverse of b over a. But it is true that tangent theta equals b over a. It's also true that a can be described in terms of r and theta, right? A is just r cosine theta. And how do we know that? Well, because cosine theta is adjacent over hypotenuse. It's a over r. So cosine theta is a over r. Solving for a, we would multiply both sides by r and get a equals r cosine theta. Similarly, b is r sine theta, right? Because sine theta is b over r. Solving for b, we would multiply through by r and get r sine theta equals b. So, really, when we're describing a complex number, a plus bi, we can rewrite a as r cosine theta, and we can rewrite b as r sine theta, and we can factor out the r, and so we see that a plus bi is equivalent to r times cosine theta plus I times sine theta. Now this, if you watched the math enrichment videos that I posted at the end of, oh goodness, what section was that? It was in chapter 3 after we finished talking about how, I think it was after we talked about graphs of trigonometric functions. And we talked about the fact that e to the x is related to sine x and cosine x by this formula, right? We know that cosine x plus I times sine x is e to the ix, right? Or if we're using theta instead of x, cosine theta plus I sine theta is just e to the I theta, or e to the theta I, however you want to say it. So this thing right here, r times e to the theta I, is called the polar form of a plus bi. Okay. Another thing to note that I didn't mention earlier is that r is the square root of a squared plus b squared. That's just Pythagorean theorem, right? A squared plus b squared equals r squared. Solve for r, and always take the positive version when you're looking at r. So r is the square root of a squared plus b squared. But the moral of the story is this, right? If you can find the distance from the point to the origin, r, and then if you can find the angle theta that this point's ray makes with the positive x-axis, then you can rewrite the number a plus bi in the form r times e to the theta I, and this is called the polar form of that complex number. So let's practice doing that. So write the following complex number in polar form. Let's do it. So the first thing I need to do, well, actually, I guess the order doesn't really matter, but we need to find r and we need to find theta. Okay, so we need to find r and we need to find theta. R, as we said, as we said on the previous page, r is the square root of a squared plus b squared. A in this case is -1, and b is also -1. So in other words, this is the square root of 2, right? -1 squared is 1, 1 plus 1 is 2. So this is the square root of 2. So r is the square root of 2. And then the other thing is that tangent theta equals b over a. That would be -1 over -1. So tangent theta equals 1. Okay? Now before you say, okay, so then theta is tangent inverse of 1, tangent inverse of 1 is 45 degrees, right? So if you say theta is tangent inverse of 1, you're going to get 45 degrees. Or we should really use radians, right? We should really use radians. So we should say pi over 4. So we should say theta equals pi over 4. Except that that's not going to be correct. Because look, theta can't be pi over 4. Pi over 4 would put you in quadrant 1. But we're at -1 minus I. We're in quadrant 3, not quadrant 1. So obviously theta is not pi over 4. It should have a reference angle of pi over 4 though. So this angle right here is pi over 4. So that means that this angle is pi plus pi over 4. 4 pi over 4 plus pi over 4, so it's 5 pi over 4, right? So theta is really 5 pi over 4. So it's helpful to draw a picture so that you're sure that you're in the correct quadrant. But yeah, theta should be 5 pi over 4. Okay, so that means that our complex number z is r times e to the theta I. There's the polar form of our complex number. Okay. Go ahead and give the video a pause and see if you can do part B on your own. Okay, I'm going to go ahead and give my solution. Okay, so I think you should get 2 root 3 times e to the pi over 3i. In this case, theta was just tangent inverse of root 3 over 3. That's because theta was in quadrant 1. Okay, but you have to be careful with that. It's not, if theta is in any other quadrant, then it's not tangent inverse, right? Okay, part C. Again, give the video a pause, see if you can do this one on your own. Okay, I'm going to go ahead and give my solution. Hold on a second. This should be pi over 6. My apologies. This should be pi over 6, of course. Yeah, pi over 6. I apologize. Yeah, that should be pi over 6, not pi over 3. Okay, but part C. So see if you can do part C on your own. Okay, here's my solution. So again, with the 2 root 3 business, right? Theta is in quadrant 4 this time, right? Right, root 3 minus 3 would put you in quadrant 4. So theta should be 5 pi over 3, right? It's got to have a reference angle of pi over 3. So this would be, it would be 2 pi minus pi over 3, right? So in other words, 5 pi over 3. Okay. Okay. E to the 5 pi over 3 I. Okay, one more, part D. I'll walk you through this one just because it's a little bit strange maybe at first. It looks a little strange. We've got z equals negative 2i. So first of all, you can say r equals square root of a squared plus b squared, right? Well, that's going to be square root of 4, which is 2. And then you can say tangent theta should be b over a. Ooh, there we have problems, right? B over a. So you might think undefined. Well, here's what's going on, right? If you draw a picture, sometimes a picture really is worth 1,000 words, right? There's z right there. It's negative 2i. So you can tell that theta is actually 3 pi over 2, right? Theta is 3 pi over 2. And not only that, but you could have seen that r was going to be 2, right? R is the distance from the origin to that point. And if you're at negative 2i, then of course the distance is 2, right? Of course the distance is 2. So if you had just drawn the picture, you could have saved yourself some trouble. But no, the distance is 2. So z is r times e to the theta I. Okay, so there's that one. Okay, we can go backwards. Going backwards is easier. Going backwards is easier. All you have to remember to go backwards is that e to the xi is equal to sine x plus I, or sorry, cosine x plus I sine x. If you remember that, if you remember this relationship, then going backwards is easy, right? So we would say z equals 4 times e to the 5 pi over 3i would be cosine 5 pi over 3 plus I sine 5 pi over 3. Okay? So then the rest is history, right? So you can do that. You can do it in your head if you have it memorized. Or you can use your calculator like I'm doing right now, because I messed up a second ago, and so I don't trust myself anymore. Sine 5 pi over 3. Negative root 3 over 2. Okay, minus root 3 over 2i. Of course, you can distribute the 4, right? So we can say z is 2 minus 2 root 3 times I. And there you go. There's the rectangular form. Now we can do the same thing with this one, right? We can say this is going to be 2 times cosine 5 pi over 4 plus I times sine of 5 pi over 4. That's 2 times cosine 5 pi over 4. Now what quadrant are we in? Quadrant 3, right? So cosine is going to be negative there. And sine is also going to be negative there. So this is really negative root 2 minus root 2i. So there's our polar version, or our rectangular version of that polar number. Okay? Very good. So now that we have practiced rewriting complex numbers in polar form, we can give de Moivre's theorem. De Moivre's theorem says this. It says if z equals r times e to the theta I, so if you've got a complex number in polar form, then z to the n is equal to r to the n times e to the n times theta I. That's not very surprising. That's kind of exactly what we would expect of exponents. We can't really take it for granted, I guess, because we never defined exponents over the complex numbers, right? Or rather, what I'm saying is the product rule of exponents says that a times b to the nth power is a to the nth power times b to the nth power. We know that this is true if a and b are real numbers. The problem is e to the theta I is not necessarily a real number, right? And so we can't take it for granted that this relationship holds. But what de Moivre's theorem tells us is that it does, right? That this relationship is still true. Exponents still distribute even across complex numbers, which is good to know. Okay. Now let's practice applying it, right? So let's say that z is -1 plus I, and let's say that we wanted to calculate something like z to the 8th power or z to the -12th power, right? In order to do this, if we leave it in rectangular form, we're going to have to multiply -1 plus I times -1 plus I times -1 plus I. We're going to have to do this 8 times. It's going to take forever. Z to the -12 would be even worse. That would be 1 over z to the +12. So then we'd have to do z to the 12th and then say what's 1 over that and try to change that back into a complex. I mean, it would just be a nightmare, right? But what I'm going to do instead is I'm going to appeal to de Moivre's theorem. And I'm going to change this into a polar form so that I can then apply de Moivre's theorem to it. And then since I was given the number in rectangular form, I'm going to give my answers in rectangular form as well. But it's going to be a lot easier to go through the polar form first to get there. It'll save me a lot of work. So first of all, r is going to be square root of -1 squared plus 1 squared. In other words, it's going to be root 2. And tangent theta is going to be 1 over -1, so -1, right? Which quadrant are we in? We're in -1 plus I. We're in quadrant 2. So there's theta in quadrant 2. So theta, the reference angle for theta is going to be 45 degrees, pi over 4. So, but we need to be over here in quadrant 2, so I think that's going to be 3 pi over 4, right? So theta is going to be 3 pi over 4. 3 pi over 4. Okay, so our complex number z is r e to the theta I. Okay, so now we can do z to the 8th power and z to the -12th power pretty easily, right? We can just say, well, z to the 8th power is going to be root 2 to the 8th power times e to the 3 pi over 4 times 8 I. Right? Root 2 to the 8th power, well, root 2 squared would just be 2. So you do that 4 times, and then you would get 16, right? So this is 16. E to the 8 will cancel the 4 and leave 2, so it's e to the 6 pi I. Well, that's interesting. Let's see what that is as in rectangular form. 16e to the 6 pi I. So that's going to be 16 times cosine 6 pi plus I times sine of 6 pi. 6 pi is just coterminal with 0, right? What's cosine of 0? Cosine of 0 is 1. Sine of 0 is 0. Whoops. So this would be 1 plus 0i. 16 times 1 plus 0i. Or in other words, just 16. Look at that. So you start with this complex number, -1 plus I. You raise it to the 8th power, and you should just get 16. That's kind of interesting. Z to the -12 is going to be similar, right? So z to the -12 is going to be root 2 to the -12 times e to the, oh shoot, I messed this up. I'm going to just use a little caret. Right, times e to the 3 pi over 4 times -12 I. So what would this be? Well, root 2 to the -12, that's 1 over root 2 to the +12. That would just be 1 over 6, or 1 over 2 to the 6th power, which I think is 64. It'd be 1 over 64. So it's 1/64 times e to the 3 pi over 4 times 12. Well, the 12 will cancel the 4, and leave a 3. So I think this is going to be a negative 9 pi I. That's interesting. Okay, negative 9 pi I. So that's going to be 1/64 times cosine of negative 9 pi plus I times sine of negative 9 pi. Cosine of negative 9 pi, now that's just coterminal with pi, right? So cosine of pi would be negative 1, and sine of pi would again be 0. Okay, so this is going to be 1/64 times negative 1 plus 0i. So that's just negative 1/64. Okay, so there's de Moivre's theorem for you. Okay, it may seem like a lot of work, but it sure beats the heck out of trying to raise this to the 8th power. Man, you'd have to do negative 1 plus I times negative 1 plus I, FOIL that out, and then multiply your result by negative 1 plus I again, FOIL that out, and then you have to do that 8 times, right? You do that 8 times. It would be a pain, and you're almost certain to make a mistake. But if you do use de Moivre's theorem, then it's a little easier. Now you may wonder, why have we taken this random detour? Why are we talking about this weird theorem when what we're trying to do is find zeros of polynomials? Well, here's what really helps us find the zeros of polynomials. It's a corollary to de Moivre's theorem, and it's about the nth roots. So let's suppose that you have some complex number r e to the I theta. The nth roots of this complex number, w, are given by r to the 1 over n. Right? That makes sense if we're taking nth roots. That's the same as raising stuff to the 1 over n power. Okay? Times e to the power of theta plus 2k pi over n. Now again, it makes sense that we're dividing by n, right? Because if we're taking the nth root, that's the same thing as raising something to the 1 over n power. So you're going to get a 1 over n. You're going to get an n in your denominator here. What's maybe a little surprising is this 2k pi business, right? What is the k? Well, k is 0, 1, 2, all the way up to n minus 1. So for example, if you're taking fifth roots, then k would go all the way from 0 to 4. If you're taking seventh roots, then k would go all the way from 0 to 6, right? So one less than whatever root you're taking. This generates a whole bunch of nth roots. It doesn't just give you one nth root. It's going to give you a different nth root for every value you plug in for k, which is good. We'll talk about it in a second. Let's just apply this corollary to de Moivre's theorem to this first problem. It says find the cube roots of negative 1 plus I. Okay, the cube roots of negative 1 plus I. Now, if you tried to do this just algebraically, you'd have to think to yourself, what complex number multiplied by itself 3 times would give me negative 1 plus I? Good luck doing that in your head. Okay, personally, I cannot do that. So what I'm going to do instead is appeal to this corollary of de Moivre. I'm going to say, first of all, I need to rewrite this rectangular number in polar form. And so I'm going to call it w. I'm going to say, well, so r is going to be the square root of, square root of 2 again, right? Negative 1 squared plus 1 squared is 2. So r is the square root of 2. What about theta? This number is going to be over here in negative 1 plus I, here in quadrant 2. I think I just did this one. Oh, we just did this one. This was example 4, right? It's the same number as in example 4, negative 1 plus I. So I already know the polar form of it is going to be root 2 plus, I already know that the number here, w, is going to be root 2 times e to the 3 pi over 4 I. Okay? So there's the polar form of that number. Now we can use this corollary to de Moivre's theorem to find the cube roots. Okay, if we're finding cube roots, then n is 3, right? We're finding the third roots, the cube roots. So n is 3. So I'm going to have 3 cube roots, right? So I'm going to say z sub k going to be r, so r is the square root of 2, right? So it's going to be r to the 1/3 times e to the power of theta, which is 3 pi over 4, plus 2k pi over n, n in this case is 3, right, times I. And k is allowed to go from 0 to 2, right? You stop at 1 less than n. n is 3, so k stops at 2. So this generates all of our zeros, right? So when k equals 0, we get z sub 0. That's going to be root 2 to the 1/3. By the way, root 2 is just 2 to the 1/2 power. 1/2 times 1/3 is 1/6. So I'm just going to call this 2 to the 1/6. Okay, so it's 2 to the 1/6 times e to the, if k is 0, then this is just 3 pi over 4 divided by 3. Right, so that would be pi over 4 times I. When z is 1, I get 2 to the 1/6 times e to the power of 3 pi over 4 plus 2 pi divided by 3. Let me see. 3 pi over 4 plus 2 pi is 11 pi over 4 divided by 3. That's 11 pi over 12, right? E to the 11 pi over 12 times I. And then when k is 2, I get 2 to the 1/6 times e to the power of 3 pi over 4 plus 4 pi is 19 pi over 4 divided by 3 is 19 pi over 12. Okay, 19 pi over 12 I. So those are the cube roots of -1 plus I. Now, if you're like me, this isn't very satisfying. It's like you want to get some sense for what these numbers are in rectangular form. So let's put them in rectangular form, right? So in rectangular form, this would be 2 to the 1/6 times cosine pi over 4 plus I times sine of pi over 4. And same thing with the rest of them. 2 to the 1/6 times cosine of 11 pi over 12 plus I times sine of 11 pi over 12. This would be 2 to the 1/6 times cosine of 19 pi over 12 plus I times sine of 19 pi over 12. And if I punch that into my calculator, let's see. So 2 to the 1/6 times cosine of pi over 4 is approximately 0.79. Okay, so z0 is approximately 0.79. And sine of pi over 4 is going to be the same. So plus 0.79 I. Z sub 1 is going to be approximately, I'm going to change the pi over 4 to 11 pi over 12. That's approximately -1.08. Plus 0.29 I, and Z2 is approximately .29 minus 1.08 I. Okay, so there we go. These are the exact answers up here, right? But if you want some approximations to see about how much this is, these are about how much this is. In other words, if you raise 0.79 plus 0.79i to the third power, you're going to get negative 1 plus I, approximately, right? We did some rounding here, so it's not exact, but you're welcome to check that on your own. And same thing here and same thing here. And one thing that you'll notice that I have said out loud, but I should maybe draw more attention to, is the fact that we have 3 roots here, right? So we're looking for cube roots, and we had 3 of them, right? We had 3 cube roots, 3 distinct cube roots. That's not a coincidence. It's true in general that you're always kind of going to have exactly nth roots. And that's something that just follows directly from the fundamental theorem of algebra. So now, let's tie all of this together. Let me show you what this has to do with finding the zeros of polynomials. And so we're going to come back to our old friend, x to the 4th plus 1. We've been looking at this since the beginning of the chapter, trying to figure out, well, how in the world do we describe the complex solutions of this polynomial? We know we should have 4 complex solutions. Well, check it out, right? We were not able to make any progress on this back in 4.2. We looked at this example. It was 1e in section 4.2, but we weren't able to do anything with it. But look at what we can do now. We can say, if I want to find the zeros of x to the 4th plus 1, then I can set this polynomial equal to 0 and then solve for x. Now, the way we usually do that is by factoring this thing. But as we've seen, we can't really factor it using any of the techniques that we have available to us. So another thing that we could do would be to move the 1 over and then take 4th roots, right? So this implies that x is going to be the 4th root, the 4th roots of negative 1. So you can see now that de Moivre's theorem is going to come in handy, or rather that corollary to de Moivre's theorem is going to come in handy, because basically in order to solve this equation, in order to find the zeros of this polynomial, we need to know what the 4th roots of negative 1 are. Okay. Well, so first of all, let's rewrite negative 1 in polar form. So, in polar form, negative 1. So negative 1 would be over here. So obviously theta is pi radians, and r is 1, right? So this would be 1 times e to the pi I. Or in other words, just e to the pi I. Actually, that's not x, that's x to the 4th. So x to the 4th is going to be e to the pi I. So what is x? X is the 4th roots of e to the pi I. Okay, so the 4th roots, let's remind ourselves, right? Z sub k is going to be r to the 1 over n times e to the power of theta plus 2k pi divided by n. K is 0, 1, 2, or 3, right? We stop at 1 less than the n, the 1 less than n, right? So these are the zeros. Or rather, this is the rule that generates the 4th roots of negative 1, which are going to be the zeros of this polynomial, okay? So let's see what we get. When we plug in 0, and by the way, r I should have just said is 1. 1 to the 1/4 power is just 1, right? So when we plug in 0, we get 1 times e to the pi over 4. I forgot the I here, but there should be an I. So it's 1 times e to the pi over 4i. Okay? When we plug in 1, we get 1 times e to the pi plus 2 pi is 3 pi. So we get e to the 3 pi over 4 times I. When we plug in 2, we get e to the 4 pi plus pi is 5 pi. So we get e to the 5 pi over 4 times I. And when we plug in 3, we get 1 times e to the 6 pi plus pi is 7 pi. So we get 7 pi over 4 times I. Okay. Well, I'm just going to write out the answer. Instead of writing out the, this is cosine pi over 4 plus I sine pi over 4, I'm just going to do that in my head. Cosine pi over 4 is root 2 over 2. Sine of pi over 4 is also root 2 over 2. So this is root 2 over 2 plus root 2 over 2i. This second one, we would be in quadrant 2, so cosine would be negative. Sine would still be positive. For this next one, 5 pi over 3, we're in quadrant 3, so they're both negative. And then 7 pi over 4 puts us in quadrant 4. Cosine is positive, but sine is negative. So what are the zeros of this polynomial? These are them, right? These are the 4 zeros of this polynomial. This is an incredible thing, because what we're saying is that the fourth root of -1 is equal to one of these 4 things, right? We don't actually have an agreed upon like which one of these is the fourth root of -1, right? They're all fourth roots of -1. All 4 of them are fourth roots of -1. Okay? But it goes to show you that this number, which we said could be rewritten as the square root of I, but that still wasn't a complex number. We were still searching for like what real numbers a and b will make it so that we can rewrite this as a plus b times I. Well, here they are, right? A is root 2, a is root 2 over 2, b is root 2 over 2. Or you could take a to be negative root 2 over 2 and b to be positive root 2 over 2 and so forth, right? But these are all complex numbers. Notice that we don't have square roots around the I or anything. These are all in the form a plus bi. So it's a really cool thing, really kind of an exciting result, I would say. And there you go. So these are the zeros. Let's do another one. Number 6 says, find the cube roots of 1 in 2 ways, by solving x cubed minus 1 equals 0 by factoring, and by applying the Moivre's theorem. Okay. X cubed minus 1 equals 0. So to find the zeros by factoring, here's what we would do. By the way, can I come back up here for a second again? What we're saying is that if you were to take root 2 over 2 plus root 2 over 2i, raise it to the 4th power, so you multiply it by itself, FOIL, right? Do that 4 times, you're gonna get -1 as the result of all that. Okay, so that's also kind of interesting. Another way to say that is that if you plug these results in for x here, you're gonna get 0, right? So if you plug in root 2 over 2 plus root 2 over 2i, raise it to the 4th power, and then add 1, you're gonna get 0. Same way with the other 3 solutions. Okay. I'll let you check that on your own if you want, but it is true. So here's another way we can verify that de Moivre's theorem works. So we'll solve this equation by factoring, and then we'll solve it by using de Moivre's theorem, and you'll see that we end up with the same results. So to solve this by factoring, we would factor this as a difference of cubes, right? So x cubed minus 1 equals 0. As a difference of cubes, this would be x, 1, x squared, x, and 1. And the signs are same, opposite, always positive. So right away we can see that one of the zeros is going to be 1. The other 2 zeros are going to come from this equation here, which we can't factor, but we can use quadratic formula. So we can say x equals 1, or x equals plus or minus, or sorry, x equals negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. So in other words, x equals 1, or x equals -1 plus or minus 1 minus 4 is -3. Square root of -3 would be I root 3 over 2. So the zeros that we get are 1, and then -1/2 plus root 3 over 2i. I'm just rearranging this stuff so that I'm taking the I out here, and I'm splitting the denominator and taking the I out in front. So we have negative 1/2 plus root 3 over 2i and negative 1/2 minus root 3 over 2i. So those are the three zeros of, or three solutions to this equation. Now let's do the same thing by applying de Moivre's theorem. So the way we would solve this using de Moivre's theorem is we would say x cubed minus 1 equals 0 implies that x cubed equals 1, and that implies that x is a cube root of 1. Now, what are the cube roots of 1? You may think, well, I can take the cube root of both sides and I get x equals 1. Well, yeah, that's one of the cube roots of 1, but there are two others, right? You should have three cube roots of 1. So what are the other cube roots of 1? Well, let's see. So first of all, I'm going to change 1. I'm going to change 1 into into polar form. Okay, so 1 is right here on the x-axis. That means theta is 0 and r is 1. So this is going to be 1 times e to the 0i. Okay, so that's not very illuminating, but now let's find the cube roots, right? So the cube roots, z sub k, is going to be 1 to the 1/3 power times e to the power of 0 plus 2k pi over 3 times I. K is allowed to go from 0 to 2, right? So z sub 0 would be 1 to the 1/3 is just 1, right? So this would be 1 times e to the 0i. Z sub 1 would be 1 times e to the, well, if I plug in 1 for k, I get 2 pi over 3. 2 pi over 3 I. And if I plug in 2, you get 1 times e to the 4 pi over 3 times I. Well, e to the 0i, we just said was 1, right? So this first 0 is just 1. But what about the next 0, right? I would have to do cosine 2 pi over 3. Cosine 2 pi over 3, negative 1/2. And then sine of 2 pi over 3 is root 3 over 2. So it's negative 1/2 plus root 3 over 2i. Ooh, what do you know, right? What about this one? I would do cosine 4 pi over 3. It's negative 1/2. And then sine of 4 pi over 3 is negative root 3 over 2. What do you know? Okay, so sure enough, I get the same answers when I use de Moivre's theorem as I do when I factor. And that's good news, because that means in situations like this one where we can't factor, we can be confident that de Moivre's theorem is giving us the correct results, right? So it's a really nice tool. Let me give you one more example. Now this is another one that we saw. This was example 1F from 4.2. I'm actually going to pull that out so we can take a look at what we did in 4.2 on that particular problem. We did make some progress on it. Okay, so here was 4.2 part F. So we made some progress. First of all, we factored by grouping. We saw that this thing was equal to x squared minus 3x plus 2 times x to the 5th minus 1. This thing factors further, but x to the 5th minus 1. Now that was a problem. We found that 1 was a 0, but then we were left with this x to the 4th plus x cubed plus x squared plus x plus 1, and we weren't able to take that down any further. We weren't able to find any more zeros. So what I'm actually going to do is I'm going to start from this point, and I'm going to use de Moivre's theorem on this piece, okay, on this piece of the polynomial. So let's write down what we have. We know from the work that we did in 4.2 that f of x is really x minus 2 times x minus 1 times x to the 5th minus 1. Okay, we got at least that far. So where do we go from there? So where do we go from there? Well, so we're going to say, if I want to, so I know that one of the zeros is 2 and one of the zeros is 1. If I want to find the other 5 zeros, then I can set x to the 5th minus 1 equal to 0 and then solve for x. So I can say x to the 5th minus 1 equals 0 implies that x to the 5th equals 1. Or, as we saw on the previous page, in polar form, this would just be e to the 0I. Okay? So, so that means that x is a fifth root. X is a fifth root of e to the 0I. Right? How do we find the fifth roots? Well, we use that corollary to de Moivre's theorem. We're going to say z sub k is equal to 1 to the 1/5 times e to the power of theta, which in this case is 0, plus 2k pi, divided by n, which in this case is 5, since we're looking for fifth roots. K is allowed to range from 0 to 4 in this case, right? So z sub 0 is going to be, well, 1 to the 1/5 is 1, right? And 1 times anything is just that thing. So I'm just going to write, this is just going to be e to the 0I. Oh, I forgot the I again. That's important, and I keep forgetting it. But z0 is just going to be e to the 0I. z1 is going to be e to the, if I plug in 1, I get 2 pi over 5 times I. If I plug in 2, you get e to the 4 pi over 5 I. If I plug in 3, I'm going to get e to the 6 pi over 5. And if I plug in 4, I'm going to get e to the 8 pi over 5 I. Okay, so those are my zeros. Now e to the 0I is just 1. E to the 2 pi over 5I, I'm going to have to do approximations here, I think. Cosine 2 pi over 5. Actually, my calculator does give me an exact answer. I'm not exactly sure how it's giving me this answer, but it's giving me an exact answer. It's telling me that this is equal to, so it's exactly equal to root 5 minus 1 over 4. And then sine is nasty. It's plus the square root of 2 root 5 plus 10 divided by 4 I. So I'm just gonna, so I'm not gonna write out the exact answers anymore. I'm just gonna give the decimal approximations. So that's approximately 0.31 plus 0.95 I. E to the 4 pi over 5. So it's cosine 4 pi over 5. That's about, it's approximately negative 0.81. Sine 4 pi over 5 is 0.59 approximately. Cosine of 6 pi over 5 would be approximately negative 0.81 again. Sine is going to be negative 0.59. And then finally, cosine 8 pi over 5 is approximately 0.31. Sine is negative 0.95i. Okay, so there we go. So what are so the instructions were to find all of the zeros. What are all of the zeros? Well, the zeros are 2, 1, right? I had a 0 of 1 there, and then it happened again there. So it's actually 1 multiplicity 2. Excuse me. So 1 multiplicity 2. That takes care of 3 zeros, right? 1, 2, 3 zeros. I should have 7 zeros. So what are the other 4 zeros? Well, they're right here, right? De Moivre's theorem gave them to us, right? So the other 4 zeros are approximately 0.31 plus 0.95i, negative 0.81 plus 0.59i, negative 0.81 minus 0.59i, and then 0.31 minus 0.95i. And there you have it, right? So we've got 7. 1, 2, 3, 4, 5, 6, 7 zeros of our polynomial. So that does it. That does it. That's how we find all of the, or that's what I should say is this. We actually still cannot find all of the zeros of a polynomial. De Moivre's theorem only helps us find certain kinds of complex zeros, right? Specifically roots of complex numbers, but it doesn't help us do much else. So there are still some zeros that we can't find using any of the techniques that we've covered. What we do in those circumstances is we try to approximate what the zeros are. And we'll talk about that briefly in the next section, but approximating zeros is not a huge topic in this class. But I will give you one way that you can approximate zeros in the next section, in case you can't find their exact formats using any of the techniques we've discussed so far. But there you go. At this point in your mathematical career, you have all of the tools in your toolkit that I know of for finding zeros of polynomials. So that's pretty cool. You've come a long way. So I'll see you in the next section.